All right, welcome, folks. Today we're going to continue developing our definition of functions and practicing graphing. Today we're teaching you what I refer to as the snail method. Later we'll teach you guys the quicker method. But I do think, fox other bug. I do think that this is a important lesson because it helps you guys to understand that a graph of a function is not specifically just a line, right? That it's representing a collection of solutions, which we'll talk about a little bit later here. Represent both linear and nonlinear contexts and be able to describe those graphs using academic terms, and then understand that a graph is just a physical or visual representation of an equation. Now, you guys have probably been exposed to many different types of graphs. Graph is a visual representation of data. And there's a lot of different types. There's a circle graph that might be used to show the 8th grade's favorite after-school activity or activity in general, like dance, dodgeball, basketball, and so on. Might use a bar graph to show how many people enjoy apples over oranges, bananas, fruits, blueberries, and grapes. Candle graphs, that's what or actually this is called a histogram. You guys maybe have made these before in your past. This is a statistical analysis. Candle graphs, that's used a lot in the financial world, but essentially graphs are just visual representations of information, which are important. A lot of people are visual people. The stock world deals with these types of candle graphs. Sometimes I buy and sell cryptocurrencies just for fun. We use these types of graphs all the time. All right. Today, what we're going to focus on is what's called the line graph. Okay, line graphs are continuous, meaning that they have straight lines that travel through the course of the entire graph itself. All right. And traditionally, on a line graph, we've got an independent variable or an x value going on the bottom of our graph itself. Okay, x is always going left and right. And what we're showing is a change in the dependent variable or the y value, which always goes up and down. All right, and we show these with ordered pairs, x, y's. All right, and just remember, x is going this way, y is going this way. Okay. Now, as we've learned in a previous lesson, okay, these can represent both linear and nonlinear functions. So today we're just going to deal with some equations that don't have a whole lot of context to them, but we just have to practice with the graphing part. All right. Now, one example. I want you guys to imagine that your rule is that one number is double the other number. Okay, an equation that might match this phrase is y equals 2 times the x. So if we pick out a couple different values of x, like 0, 1, 2, and 3, that to come up with our y values, we just need to double the input. Okay, again, think of x as your input and y as your output. If we double the number 0, we get 0. If we double the number 1, we get 2. If we double the number 2, we get 4, and so on. Now, what we've just done is collected a whole bunch of order pairs that we could then throw into a graph. 0, 0, 1, 2, 2, 4, and 3, 6 that can represent the function double a number. Okay. Now, graphing it, super slick and easy. Okay, we find each location, put a dot, and then connect the dots. So let's find 0, 0. This is called the origin, by the way. Okay, the middle of our graph is called the origin because it's when, it's where both of the horizontal and vertical lines originate from. And in this situation, we're including the origin, 0, 0. 1, 2 is 1 unit to the right and 2 units up. This is another location that represents a solution to the equation y equals 2x. 2, 4 is to the right 2 and up 4. So we've got another location. 3 and 6. The next one would be 4 and 8, and so on. 5 and 10. All right. Now we're not going to try and represent every solution to y equals 2x. We're just going to show some of them. All right. This is a linear function. Again, we've got a consistent change. The x is being raised to the first power, or we don't see an exponent attached to the x. And the line continues forever. All right. So this is what we're going to practice with today, is just graphing any function using the snail method, which essentially is make a table of the solutions, and then graph them. Okay. Now, a couple hints. Try and pick some positives and negatives when you make your tables for your x values. I always suggest as inputs, -2 through +2. There's a couple exceptions to that rule, but -2 through +2 can accurately show on both sides of the y-axis how the graph is interacting. Okay, this is a really good table that you guys can use where there's the x value, there's a little spot for your work, and then the y value that results from it. And then you throw it onto this graph. All right, so I think this makes most sense when it's shown in practice. So that's what we're going to do. First one, super easy, y equals x. This is, by the way, called the parent function. Let's pick out some easy values of x. Okay, the work on this is just to say, all right, y is equal to my x value of -2. Y is equal to my x value of -1. Okay, so I've done my work, and now I just plot them. -2, -2 is to the left 2 and down 2. It's right there. -1, -1, 0, 0, 1, 1, 2, 2. Okay, so we've got a whole bunch of different coordinates that satisfy the equation y equals x. Like I said, this is the parent function. Okay, the challenging thing is what happens when we start to manipulate the parent function? What happens when I say y is equal to double the x, or half of the x, or double the x plus 4, right? That's what we'll get into. All right, like this one. We're going to take -2 times the x and then add 4 to it. So again, I think it's wise to pick out some positives and negatives, right? And in my work portion, I'm just going to submit those x values to the equation. -2 times -2 plus 4. -2 times -1 plus 4. -2 times 1 plus 4. -2 times 2 plus 4. All right. Now, gotta actually do the math. -2 times -2 would come first because of PEMDAS. That's 4. 4 plus 4 would get me 8. Okay. -2 times -1, that's 2. 2 plus 4 gets me 6. -2 times 0 is 0. 0 plus 4 is 4. This is -2 plus 4, which would get me +2. And you guys can start to see here, if you're doing your math correctly, you should get a little pattern that's forming. Right? And that pattern that you see is that the y values are always decreasing by 2 per x. Right? It's not by accident, it's because of the number that's in that spot. Right? Now all I need to do is treat each one of those like ordered pairs. So I've got the ordered pairs -2, 8, -1, 6, 0, 4, 1, 2, and 2, 0 that I need to throw onto this graph. -2, 8 is to the left 2 and up 8. Here's my first point. -1, 6 is right about there. 0, 4 is right about here. That's called the y-intercept, by the way. 1, 2 is right there, and then 2, 0 is right there. And look at that. Straight line function. Okay? Straight line or linear function. Now this, again, is called the Snell method. We will teach you a quicker way to do this in the next unit, all right? But I think it is important to understand that each of these points represents one solution. One solution of an infinite amount of solutions as well. All right? Half x minus 3. Okay, so again, we can pick out those same inputs. There is one little trick with this if you wanted to, but I'm going to skip that trick. Just for consistency, -2 as my x value, I need to take half of that and then subtract 3. This is a way that I like to do it too. Half of something minus 3, half of something minus 3, half of something minus 3. A good idea is to just leave that space open and then just plug it in later. So this is -2, -1, 0, 1, and 2. And then do the math. Half of -2 is -1 minus 3 would get me -4. A half of -1 is -0.5 minus 3 is going to get me -3.5. A half of 0 is 0 minus 3 is -3. Half of 1 is 1/2. Keep it consistent, use a decimal. 0.5 and then subtract by 3 is going to get me -2.5. And then a half of 2 is 1 minus 3 is going to get me -2. So I've got all of my ordered pairs here. -2, -4 is 2 units to the left and 4 units down. I'm going to have to scroll a little bit. 2 units left, 4 units down. -1, -3.5 is going to be about right here. 0, -3 is going to be about right here. 1, -2.5, about right there. And 2 and -2. So my graph of this straight line function is looking something like this. So hopefully you're catching on to this. The snail method literally is just plug in a number, do the math with it, and get your output or get your y value from that. All right. Why don't you guys pause the video and try this one all on your own. 7 minus 3x, so create your table. Attempt to graph it on your own. And then you compare it to my work here in a second. You guys have to have at least 5 points. That's kind of required by us. I think the easiest 5 to choose are -2 through +2. That's just me. You guys choose what you'd like. All right, let's do the math on this now. So we got 7 minus 3 times a number, 7 minus 3 times a number. Plug in my values. I got -2, -1, 0, 1, and 2. Now I just need to do the math. 7 minus 3 times -2 or -6. 7 minus 3 times -1 or -3. You guys got to be really careful with your addition and subtraction here. 7 minus 0, 7 minus 3, and 7 minus 6. This one, I think it works better to work from the bottom to the top because the calculations are a little easier. 7 minus 6 is 1. 7 minus 3 is 4. 7 minus 0 is 7. Now you kind of see the little pattern that's forming here as we go up the chart. Numbers are increasing by 3. Let's see if that continues. 7 minus -3 is the same as 7 plus +3, so be careful. That would get you 10. 7 minus -6 is the same as 7 plus +6, which is 13. Okay. So -2, 13. If your numbers don't occur on what you're given, you can just estimate it. -2 and 13. 13 is going to be somewhere way up here. Or just do what you can. -1 and 10 should show up on our graph. That's going to be right up here. 0, 7, 1, 4, and then 2, 1. So our graph for this function will be linear again, fairly steep going down and to the right. Now, we also can use this technique for some nonlinears, and the process doesn't change. It's just your graphs look a little bit different. We should still pick positive and negative values of x. So I'm going to choose the same 5. Okay. It's just ultimately a lot more important to pay attention to signs and pay attention to order of operations when you're dealing with equations like this, equations that maybe have an x squared to them or an x to the third power, or even a 2x squared. So let's do our x squared minus 5. So I'm going to take a number to the second minus 5. Plug in my -2 through +2. So we got -2 to the second, -1 to the second, 0 to the second, 1 to the second, 2 to the second. Little hint here, by the way, for those that like to use calculators for this type of stuff, make sure that your input is in parentheses, otherwise you may get the problem wrong, okay? But -2 times itself gets you 4, and 4 minus 5 is -1. So I got first set of input and output. -1 to the second power. -1 times -1 is 1, minus 5 gets me -4. 0 to the second is 0, minus 5 gets me -5. Now there's going to be kind of a fancy little thing that happens when we plug in 1. 1 to the second power is 1 minus 5. Notice how it's the exact same calculation as -1 to the second minus 5. Okay, not by accident. 2 to the second power is 4 minus 5, and you get -1 back as an output. So this is one of those, what's called a parabolic function. Parabola is anything that has an x squared within that function. So let's find those locations. -2 and -1, it's right here. -1, -4 is down here. 0, -5 is about right there. And what you'll see here is when you look at the x value of 1 and -4, it's got the exact same output as or -1 and +4, or -1, -4, excuse me. -2, -1 is right here. So you can see that these points kind of take a dip and then they come right back up. All right. Anything that has that x squared is going to have a U shape. All right. But process did not really change all that much. I still picked out the same inputs to plug in. It just was a little bit different finding the outputs. Okay. -2x cubed. So I'm going to throw in -2 through +2. Again, be really careful about showing this correctly. So we got -2 times the number to the third, -2 times the number to the third, and so on. Plug in my values, and then do my math. Now, be careful here. Okay, the tendency is to work outside of order of operations when we're doing this, but make sure that we understand exponents come first. So I need to do -2 to the third power before I multiply the -2. So let's try this. -2 times -2 is 4. 4 times another -2 is -8. So essentially what I'm doing here is -2 times -8. -1 to the third power. -1 times -1 is 1. 1 times another -1 is going to get me -1. So I got -1 times -2 times -1. 0, finally an easy one. That's just 0. 1's a little easier as well. 1 to the third power is just 1. And 2 raised to the third power, a little bit easier. That's -2 times 8. Okay? So when we do the math on this, -2 times -8 is 16. -2 times -1 is 2. -2 times 0 is 0. -2 times 1 is -2. -2 times 8 is -16. Now, if you need to, you can always switch the values of your y's. Like in this one, we got 16 and -16. All I'm going to do is I'm going to change this to be 2, 4, 6, 8, and so on. Okay, so each one is now worth 2 units. I'm going to save myself the time on the bottom side, just assume you guys get that. -2 and 16 then is going to be somewhere right up here. -1 and 2 is going to be about right here. 0, 0 is right in the middle. Now, maybe I will change these just so that we have it clear. This is -2, -4, -6. Now, let's see, 1 and -2 then would be here, and 2 and -16 is right down here. This is one of those kind of a S-shaped functions. So it takes that look to it. All right, definitely nonlinear. It's got a curve to it, and you can also see why it would be nonlinear from the equation, the x cubed part, and from the table. Okay. So, long story short, pick out those values of x, plug them into your equation, come up with your ordered pairs, and graph them. That's about the essence of the lesson today. Have fun.